On the night of June 1, 2009, an Airbus A330 operating as Air France Flight 447 departed Rio de Janeiro for Paris. 228 people were on board. The departure was routine. The aircraft was almost new. The flight crew was qualified. The weather over the Atlantic was rough, typical for the region, but not extraordinary for a commercial airliner. The mechanical anomaly at full load was remarkably brief. 3 exterior sensors iced over for less than a minute. Less than a minute, from the moment that ice formed to the moment the aircraft struck the ocean, was 4 minutes and 23 seconds. The aircraft plunged into a specific hazard hidden within the upper layers of the equatorial atmosphere, triggering a cascade of automated system disconnects. While 32 other flights had experienced this exact failure mode and survived, the physical parts that might have changed the outcome for Flight 447 arrived at Air France's hangar in Paris 6 days earlier. They were simply waiting in a box. The aircraft that became Flight 447 had not yet been touched. This is a disaster engineered through the slow accumulation of regulatory compromises, maintenance schedules, and deeply conditioned training reflexes. The investigation centers on a tube no longer than a man's forearm, mounted in the slipstream. This is a pitot probe. The specific model installed on Flight 447 was the Thales AA, a component used across hundreds of commercial aircraft. A pitot probe works on a simple physical principle. Air pressing into a forward-facing opening creates a pressure higher than the surrounding static atmosphere. The difference between those two pressure values is fed into the flight computer and becomes the number on a screen in front of the pilots: 270 knots, 300. It is the primary source of indicated airspeed. At altitude, the outside air can drop to -50 Celsius. Water freezes instantly to any metal surface in the slipstream. If the pitot tube clogs with ice, the pressure differential collapses and the airspeed reading is lost. To prevent this, every airliner has at least 3 of these probes, and they are continuously heated. The heating element is designed to vaporize moisture on contact, keeping the inlet clear in all foreseeable conditions. The safety model of airspeed measurement relied on the assumption that the heater's thermal output would always outpace the rate of ice accumulation. By the spring of 2009, data showed that the Thales AA probe was no longer meeting that assumption. The breaking point for these probes existed at 35,000 feet within the intertropical convergence zone. This belt of massive thunderstorms ringing the equator generates a specific atmospheric state. Most aviation icing involves supercooled liquid water freezing onto a wing. The industry has dealt with this effectively for half a century through de-icing trucks and wing heaters. What happens inside the upper layers of tropical thunderstorms is called ice crystal icing. Here, moisture exists only as tiny, dry, solid crystals suspended in invisible clouds. The Thales AA probe passed its certification. However, those regulatory tests were designed around liquid water icing. They did not catch the behavior of microscopic solid ice crystals at high altitude. When the rate of crystal accumulation exceeds the probe's heating capacity, a temporary slush forms inside the inlet. The pressure reading is corrupted, and the aircraft is rendered temporarily blind to its own speed. The hardware did not break. It encountered an environmental state it was never legally required to survive. The condition usually resolves itself within a minute as the aircraft flies out of the affected cloud layer, but for that minute, the airspeed indication is unreliable. The Thales AA probe's vulnerability was documented by Airbus and several airlines long before 2009. The pattern was specific and recurring. Incident reports described high-altitude autopilot disconnects followed by a safe recovery. Flight crews would hand-fly the aircraft for about 45 seconds until the probes cleared and normal indications returned. To address these reports, the European Aviation Safety Agency, or EASA, used a risk matrix to map the frequency of a failure against the severity of its outcome. Because previous flight crews successfully hand-flew through the failure, EASA concluded that the AA probe was a known nuisance rather than a flight safety hazard. This meant the replacement program remained recommended, not mandatory. Operators were free to schedule it on their own timeline. Between 2003 and 2009, there were 32 airspeed events traceable to pitot icing. 8 occurred in the 2 months immediately preceding the accident, roughly 1 a week. The aviation system was essentially normalizing deviance. Because previous crews had managed the failure mode, the regulator allowed a known hardware flaw to persist as an optional fix. Airbus had issued a bulletin recommending a replacement, the Thales AA probe. It used a different internal geometry and a more aggressive heating element designed to resist ice crystal accumulation. By early 2009, Air France shifted its internal policy, treating the older AA probe as a serious problem worth solving. They placed an order to replace the units across their long-haul fleet. The logistical timeline moved quickly. The parts were ordered, and the first batch arrived in Paris on May 25th. The first A330 was rolled into the hangar for modification on May 30th, but the Air France schedule called for the A330 registered F-GZCP to depart Rio de Janeiro as Flight 447 on June 1st. That tail number was still waiting further down the installation queue. The catastrophic outcome was dictated by a mundane administrative reality. The specific aircraft was dispatched with the old, flawed probes because it was simply not yet on the active modification list. It missed the upgrade by 6 days. At 11 minutes past 2 in the morning GMT, heavy ice crystals overwhelmed the probes on Flight 447. The heaters could not keep up. The flight computer's primary defense is its voting logic. It compares the 3 airspeed inputs, sees they are inconsistent, and rejects them all. To prevent the aircraft from acting on bad data, the computer disengages the autopilot and the auto thrust. It reverts to alternate law, a state where many automated protections are removed. The system behaved exactly as it was designed to. Aerodynamically, the aircraft was completely fine. It was flying straight and level at cruise thrust without a speedometer. The pitot probes were the only sensors failing. The aircraft still knew its pitch, its bank, its altitude, and its vertical speed. A trained pilot could fly the aircraft on those readings alone while waiting for the probes to clear. The unreliable airspeed procedure in the manual called for a specific pitch attitude and press setting. Hold the nose at 5 degrees up and maintain climb thrust. Crucially, the autopilot was basically already flying this configuration at the moment of disconnect. The system safely handed the pilots a stable flying aircraft. Survival required only that the crew maintain that stability and do nothing drastic. Instead, the pilot flying made a control input that should not have been made. He pulled back on the side stick, commanding a climb that bled off critical airspeed. That fatal maneuver traces back to simulator conditioning. Historically, unreliable airspeed scenarios were taught at low altitude during takeoff. In that environment, pulling the nose up to climb is a required life-saving reflex to avoid striking the ground. At 35,000 feet, the physics change. The margin between flying speed and stall speed narrows. Pulling the nose up at high altitude bleeds off energy rapidly, leading directly to a stall. Prior to 2009, pilots were almost never placed in a high-altitude, unreliable airspeed scenario in the simulator. It was a training blind spot. The pilot executed a deeply conditioned reflex. He used a trained response that was effective near the ground, but proved fatal in the stratosphere. Following the recovery of Flight 447, regulatory bodies closed the gaps in hardware and training. EASA issued an emergency airworthiness directive, making the BA probe modification mandatory, and the training industry overhauled its syllabus to include high-altitude pitot icing events. The combination of hardware vulnerability and inconsistent training, what defined the conditions of 2009, no longer exists in that form. But the case leaves an enduring question. What is the acceptable number of warning signs before a recommendation becomes a mandate? 32 events, 8 in 2 months, 1 a week. There is no clean number. The replacement probes that arrived too late for Flight 447 are now held in a museum exhibit at the BEA headquarters in Paris. They serve as a physical record of what was known and when it was known. The file demonstrates that safety margins are contingent on thermodynamic limits, the speed of bureaucratic intervention, and whether training scenarios accurately reflect high-altitude flight physics. If you found this analysis useful, consider subscribing to the channel. Every video here works from primary sources and official accident reports. A like helps this video reach others who care about how the record is built. If you have a suggestion for a future case file, leave a comment below. Thank you for spending this time with the file.